Fantastic. Well, thanks very much for the intro, James, and thanks Steve for asking me to speak. I'm not quite sure, well, I wasn't sure about how to pitch this, but what I'm going to do is, well, with part of the double act, so I'm going to introduce the topic of pollution, and Sheena's going to discuss the impact on health side of things. And really, it's a series of adverts for the sorts of things that we do in the Centre for Atmospheric Sciences in the School of Earth and Environmental Sciences. Because our name changed, so we've dropped atmospheric now.
It's Earth and Environment.
So yeah, we'll come back. Anyway, so this is work that's based around stuff that's been done from my group and others in the Centre for Atmospheric Sciences, the groups of James and Hugh, with Rami and Dave as National Centre for Atmospheric Science scientists in the Centre for Atmospheric Science. Now, changing air quality and the impact on health was the title we were given. As I said, I'm going to talk about the changing air quality, but largely since the Industrial Revolution, the changes in air quality have been positive, for the better, largely. The distinct and discrete plumes of pollution that were seen from the very heavily industrialised sort of the industrialisation from the 18th century onwards have largely gone, to be replaced by the foggy smokes that we get viewed from North Campus here, but largely without the discrete plumes. What I'm going to do is give a brief intro to the changing air quality and say something about how we find out about air pollution. And please ignore the blatant adverts, but I'm talking from my experience and my perspective. So, what we do, we study largely particulate matter in our centre, with some focus on gas phase processes, but with a large focus on particulates. One of the motivations is that it's the single most important contributor to air quality degradation in terms of health effects. With the COMIAP study recently suggesting that 340,000 years of total survival time lost in a single year in the UK, which corresponded to 29,000 annual premature deaths. And more likely, that's 200,000 lives shortened by a smaller amount per year. Higher in number than 116,000 attributed to alcoholism, obesity and smoking, which I found very surprising when I read it. Not my statistic. Estimated cost of particulate material in the UK of 15 to 40,000 per emitted tonne in terms of mortality, with the OECD reporting a cost to the UK of 56 billion, with the WHO estimate revised upwards to 62 billion. And I'm not sure how much of that is the Brexit exchange rate relationship. But in addition to increasing PM 2.5, diesel particulate is likely more toxic per unit mass owing to higher concentrations of toxins, including polycyclic aromatics. So there are obviously contributions from more benign particulates, but we can't separate out their effects. So what are our air quality metrics? Well, the national air quality objectives to hit the European directives are split into annual means and 24-hour means for particulate matter smaller than 10 microns in diameter or smaller than 2.5 microns, and nitrogen oxides. And these various limits have been set, and these are legal limits for the UK. Right, but we're not doing very well because London exceeded its annual number of exceedances in the first 5 days of this year, with 24 NOx exceedances when it was only allowed 18 by 6th of January. And the government's currently being challenged through the UK courts over this breach, and we will be fined by the EU, notwithstanding Brexit again. And in 2016, the annual mean limit for NO2 pollution was broken at 59 of the 97 London sites which it was measured. But this isn't just a UK problem. The WHO estimates that around 6.3 million deaths per year are attributable to indoor and outdoor air pollution, with the problems in the UK paling into insignificance compared to a lot of the developing world. And a good graphic here from the WHO showing that roughly, part of the data that shows that roughly 90% of global urban population breathes unsafe air. And you can see here, split down into the regions, the levels of particulate matter less than 2.5 microns in diameter. And you can get these sorts of charts if you follow this link for each of the individual regions. I'll go into some of the points here from the very high loadings. This is Mauritania, this one's Saudi Arabia. They're actually natural pollutants contributing to the high loadings that we couldn't do very much about even if we changed all the practices in those regions. And we'll come on to that a little bit later. But if you look, there's a couple of examples. Beijing in January 2017, we were just there in December last year measuring the sorts of pollution that we're seeing here. There's a good video there. I'm not going to try and link to it because it does all sorts of problems, causes all sorts of problems on the computer. But basically the air apocalypse, where you're seeing these waves of pollution building up during the heavy smogs. But there are very striking differences in the appearance of pollution events and their nature. So it causes very great difficulty in our understanding of the types of pollution and the causes of pollution. So here's Tiananmen Square, taken from the same point, and it's run out of the battery. So Tiananmen Square showing the change in visibility from different pollution events. And here, a distinct capping inversion showing the fumigation during this particular smog outbreak. And here, some Indian kids engaging in a national pastime in November 2016, where it seems as though there's a competition for the world's most polluted city. Delhi, in this particular instance, coming up with an air quality index, which is an amalgamation of the NO2 and PM metrics, and in clear, a clearly much higher pollution event in November in Delhi than in Beijing. So, what's the cause? Only being slightly flippant by putting a car badge up, because traffic does cause a lot of the pollution. There's a lot of industrial sources on top of this. But what I want to do is just give a bit of a brief background to the different sorts of pollution events that have been experienced. And go back to the sort of classic first example of the Great London Smog of 1952, which was a primary emission and meteorology-driven event. So emissions into a very slack condition, very strong anticyclone in the winter, caused this fumigation across London with very, very high levels of coal tar smoke and SO2, leading to the consequent increase in the number of hospital admissions and deaths. And this led to the Clean Air Act of 1956. And so measures were taken to reduce those sorts of primary emission-driven fogs, smogs. Now this I thought was 2 photos. It's not. It's actually 1 photograph of Almaty city in Kazakhstan, where there is the primary emission-driven, meteorology-driven smog is exacerbated by the photochemistry, where you produce secondary pollutants from the action of sunlight on the smog, on the primary emissions, and you cause secondary pollutants, ozone, aldehyde, particulate material, etc. And so that invigorates and causes a much denser smog. And it's not just a ground level thing. Here you can see from the space shuttle an elevated smog layer, very, very large extent. And it's a long-range transport, not just surface level problem, but elevated problem, where you have a combination of dust, as shown here in orange, carbonaceous emissions, as shown from the forested regions in South America and Africa, sea salt, as shown in the blue, man-made pollutant emissions, as shown in the white, and they're all mixing together. And if you look at the Saudi Arabian problem and Mauritanian problem, they're all caused, or very largely caused, by the dust storms. So we couldn't do very much about that, even if we tried. So the pollution isn't just a man-made problem, it's a man-made exacerbation of natural phenomena as well. You can see very startling movies of the patterns of the long-range transport. So here's where the adverts really start. How do we work out what's happening? So what we do is we go around and measure. And we measure from ships, ground-based stations, aircraft, pretty much everywhere. Clean, polluted, different emission sources, and try to characterise in large collaborations the gas phase processes and particle phase processes that are going on and contributing both to the air quality degradation and also the air quality climate interactions. Just a couple of slides more of fancy photos with some pretty impressive flying across the pristine forest, but also during burning periods to characterise the pollution that's experienced, or the pollution in the background concentrations. And we measure with a very heavily instrumented payload, with a very heavy instrumentational payload on whatever platform. Obviously ground-based and shipborne, we can carry more instruments than we can on the aircraft. And we try and access wherever we need to go with the research-grade instrumentation. And it's done in collaborations, not just UK, but these are international collaborations to capture the long-range transport, because air pollution doesn't just respect any national boundaries. What it does, we've got to have both local regulation and intergovernmental collaboration on air quality objectives in order to try and address a lot of these problems. We can go and measure and look for the individual source contributions, long-range transport and local. And the sorts of things that you can come out with, I mean, these aren't mainly airborne, these are ground-based measurements, but these are the sorts of measurements that indicate what the composition of the individual particulates are made from. Here we've got sulfate in red, nitrate in blue, ammonium in orange, but all of the rest, the greys and the greens, are all different types of organic material. And these are all different sorts, different sources of organic carbon found in the particulates. And this is in fine particulate, finer than PM2.5, so it's PM1, finer than 1 micron in diameter. And so we have this bunch of measurements, and we can identify the different pollutants from different sources, but then we need to understand the detailed processes. So how do we do that? Well, we've got a big bag, really. It's a Teflon bag, which we can illuminate with arc lamps and halogen lamps, and inject individual ingredients. So we take away the metrology, and we see what happens to the different mixtures that we put in the bag. And we can inject emissions from plants. So this is figs, we're looking at tropical forest in this particular instance. Or from engines, so we can squirt the emissions from the exhaust. And we can look at what happens to subsets of the atmospheric composition. And use research-grade atmospheric instruments, so the same instruments that we take out into the field, we can employ on our bag of air. It's acronym soup here. I'm not going to talk about the acronyms, not going to expand on this, but basically we take all of those instruments and we sample through the floor, which is where our chamber is located, with the various online and offline instrumentation to find out something about the processes. So I'll just give a quick snapshot of the sort of things we're looking at. So we took a diesel engine and squirt the emissions into the bag, turn on the lights, cook them, and see what happens to those emissions with time. And you can characterise as a function of the engine load, the amount of nitrogen oxides, or the particulate mass, or the particulate number, and we can say something about what will happen for different driving cycles and how that will change in the atmosphere. When you turn the lights on, at time 0 on this scale here, you can measure the mass spectrometric fingerprint of the individual of the particles and see how the different fragments change. And you can see here the change in the mass spectrum, and there's a change to the particular indicative fragments. And you can map this onto the space that you would see in the atmosphere, which is delineated by the dotted lines on these graphs. And these are a whole range of experiments on the top shown from biogenic injection into the chamber. And these are from man-made emissions injected into the chamber. And we can characterise what's going on dependent upon the sorts of conditions, and monitor the changes in the particulate from subsets of what you find in the real atmosphere. And you can map from offline analysis, two-dimensional GCMS, the individual components that you will find under cold idle conditions from an engine to warm conditions from the engine. You can see there's a very different sort of profile of the emissions dependent upon the conditions of the emission source. I won't go into that. And then we can look at the particulate response to those volatile organic compounds that are found under cold start and warm start, and see the different sorts of components that are emitted. So PAH is up there, ketones, aldehydes, the classes of alkanes along the bottom. And what we can do is map out this across the whole range of different conditions. And then we try to understand what goes on in the chamber. So we go out and measure in the real atmosphere, we isolate in the chamber, and we characterize in the chamber, and then we try to model what's going on inside. So we have a very complex model of the detailed chemistry and the microphysics of the particles. And you can see here, again, is the time through an experiment. These are measurements. This is the number of particles. They decay with time as they get lost to the wall of the bag. This is the mass of the particles. And in order to get particles increasing in mass, as there's decaying in time, you can see that the particles grow. This is the distribution of particles moving up here. So we put all of our best understanding of the chemistry and the physical evolution into a model, and we can see here the evolution, and the dotted line is the measurements, and mass and number again, and everything else is a simulation on here. You can see we can do a pretty good job, and you can see as we move through the simulation, the composition of the particles is predicted here using a fairly complicated master chemical mechanism with a few tweaks, which I'll not go into here, but I can discuss offline if anyone wants to. So we can do a reasonable job of replicating and understanding what's in the bag. And so, how does this help us in understanding what's going on in the atmosphere with all of this detail? Well, first of all of the detail is largely captured in this tool that anybody can access and freely available through a web front end. It's run by Dave Topping, hosted by Dave Topping in our group. So we take all of those details and try and put them into a big model to try and replicate what we're going to see in the real world. And here we're looking at biomass burning emissions evolving through the atmosphere in South America during the biomass burning season in the Samba project headed up by Hugh Coe. And it allows us to do some continental scale modelling, including the detailed processes. These are just carbon monoxide emissions, which correspond largely to the organic carbon and the black carbon emissions. So they're relatively inert, but it gives us some indication of the distribution of components. But it's no good just doing the modelling, because we can come up with any numbers we like. We've got to compare with the measurements. So taking the aircraft down, and you can see the aircraft flight track. And if the aircraft flight track is lost in the background, which are the model simulated values, then we're doing a good job with our understanding. So there's different interactions with water vapour in the moist atmosphere in Amazonia, different assumptions about the chemical processing, and we try to understand, get our best understanding of the processes that are taking place in order to explain the measurements. And that gives us some confidence that we're understanding the processes properly. We've done the same thing for the UK. So we're testing different mechanisms. So CRI here and CBM, they're just different chemical mechanisms, predicting the NO2, the ozone, nitrate radical, and comparing the nitrate radical at different levels. And I think, okay, let's go and compare these with the aircraft, because there are some distinct differences in the chemical schemes. We should be able to test which is the right chemical scheme. And again, the same thing. If the flight track disappears into the colour of the model simulation in the background, we're doing a reasonable job. And these are the sorts of games we can play to test our best understanding and incorporate it into the models which we can employ at national, regional, local scales. So here's simulation of the UK NO2 concentrations from the middle of last year. You can see very discrete and distinct plumes, but they're polluting areas, not just where they're emitted. This includes the photochemistry and the emissions. And so the exposure is going to follow this convolution of the meteorology and the emission and the chemical process. And this is included in the model that we run on ManUnicast. And a much, much finer scale, down to 1 kilometre grid spacing, we can actually see the main arterial roads in Manchester. So if you nest the simulations down, you can see here, in this simulation, you can see the M60, but you get the diurnal cycle. Come on. So essentially, you see the M60, I'm just going to picking up. Okay, and then you're advecting the pollution from Manchester across the Pennines and fumigating Leeds and Sheffield. Which you might say is okay, but maybe they'll have a different opinion. But these high-resolution simulations allow us to make predictions which can then be used to interpret the impact of the tube stream.